You tap your card at a coffee shop. In under 300 milliseconds, your bank in New York authorizes a transaction routed through Virginia, scored for fraud by a machine learning model, and confirmed back to a terminal in Tokyo. That happens 65,000 times every single second on Black Friday. Visa's entire network is allowed less than 32 seconds of downtime per year. That's 99.9999% uptime. In 2018, a single hardware failure in Europe blocked 5.2 million transactions in 10 hours. This is the hardest distributed systems problem running in production today. Let these numbers land. Visa handles $14 trillion in payment volume every single year. At peak, Black Friday, Super Bowl Sunday, it processes 65,000 transactions per second. Its tested capacity is 100,000 TPS, giving 54% headroom above holiday peaks. That headroom is not an accident. It is deliberate over-provisioning. Normal daily peak sits around 24,000 TPS. The jump to 65,000 on Black Friday is nearly 3x in hours. The system must absorb that spike with zero degradation. Now here's where it gets interesting. Authorization must complete in under 300 milliseconds across up to 4 separate institutions. Think of Visa like the postal service between banks. It does not hold your money. It routes messages. Every transaction touches exactly 4 parties. The cardholder has a Chase Visa card. Chase is the issuing bank. It holds the money and approves or declines. The merchant banks with Stripe or Square, that is the acquiring bank. VisaNet sits in the middle, routing authorization requests between acquirer and issuer. These 4 parties never share a database. They are entirely separate institutions. Visa is the trusted intermediary that makes them interoperate. This model is why your Chase card works at a merchant banking with HSBC in Singapore. Here is every hop inside that 300 millisecond window. The merchant terminal sends an ISO 8583 binary message to the acquirer, Stripe, Square, or Bank of America Merchant Services. The acquirer forwards it to VisaNet. VisaNet parses the message, reads the first 6 to 8 digits of the card number, the BIN, to identify Chase as the issuer. It runs fraud scoring in under 100 milliseconds. Then it forwards the request to Chase. Chase checks the balance, applies its own fraud rules, and returns approve or decline. VisaNet relays that response back to the acquirer, then to the terminal. Total elapsed time, under 300 milliseconds, across potentially 4 countries. Every authorization message on VisaNet is encoded in ISO 8583, a binary protocol standardized in 1987. It is older than the World Wide Web. It is still processing trillions of dollars daily. The message has 3 parts. The MTI message type indicator is 4 digits. 0100 is an authorization request. 0110 is the response. Then a 64-bit or 128-bit bitmap where each bit flags whether a data field is present. Then the actual data elements, card number, amount, merchant category code. An ISO 8583 message is 200 to 400 bytes. The equivalent JSON is 2,000 to 4,000 bytes. At 65,000 TPS, that is the difference between 26 megapersecond and 260 megapersecond of network traffic. This is why engineers lose sleep. A user double taps their card in 200 milliseconds. Without idempotency, both authorization requests go through. The account goes negative. At 0.0001% failure rate at 65,000 TPS, that is 65 fraudulent double spend transactions every second. Stripe solves this with idempotency keys, a unique hash of the transaction fingerprint stored in Redis before processing. If the same key arrives twice, the second request returns the cached result immediately. No second database write, no second authorization. The key is derived from card number, amount, terminal ID, and timestamp truncated to a 5-second window. Here is the production pattern. Every authorization request flows through a strict decision tree. First, idempotency check. If this transaction was already processed, return the cached result immediately. No bank contact required. If it is new, parse the BIN to identify the issuing bank. Run Visa Advanced Authorization Fraud Scoring under 100 milliseconds. If the fraud score is above threshold, decline immediately without contacting the issuer. Otherwise, route to the issuing bank. The issuer checks available balance and its own rules. Approve or decline. The response travels back through the same path. Every node in this flow has a timeout. A non-response from the issuer after 200 milliseconds triggers a stand-in approval by VisaNet itself. Visa's Advanced Authorization, VAA, scores every single transaction for fraud risk. It has under 100 milliseconds to do it inside the 300 milliseconds authorization window. At 65,000 TPS, that is 65,000 ml inference calls per second, around the clock. The model evaluates your historical average transaction size, the merchant category code, your typical geographic location, device fingerprint if present, time of day patterns, and velocity, how many transactions you've made in the last 60 seconds. Visa's fraud detection prevents an estimated $25 billion in fraud annually. But here's the catch. The model must never add latency that pushes total authorization past 300 milliseconds, or merchants see cart abandonment spike 30%. The 2018 Visa Europe outage lasted 10 hours. A single hardware component failed during a routine data center switch. The architecture lacked sufficient active-active redundancy at that tier. 5.2 million transactions were blocked. UK merchants lost an estimated £56 million. That incident drove Visa's current design. Today, two primary processing centers, Ashburn, Virginia and Highlands Ranch, Colorado, both process live traffic simultaneously. Every authorization record is synchronously replicated to both data centers before the response is sent. If Ashburn disappears right now, Colorado absorbs 100% of load instantly, no failover delay, no manual intervention. Think of it like two pilots flying the plane at the same time. Either can land it alone. Most engineers conflate authorization and settlement. They are completely separate systems with completely different scale requirements. Authorization is real-time, under 300 milliseconds, 65,000 TPS, no money moves. It is a reservation. Think of it like a hotel holding your credit card. Settlement is when actual money moves, and it runs on batch processing. Clearing happens at T+0 to T+1. Transaction details are exchanged between acquirer and issuer. Settlement happens at T+1 to T+2 via Fedwire, CHIPS, or SWIFT. VisaNet's multilateral obligations. If Chase owes Stripe $1 million and Stripe owes Chase $800,000, only $200,000 actually moves. This netting dramatically reduces interbank wire volume. Financial transactions demand atomicity. Either the debit and credit both happen, or neither does. The problem: Chase and Stripe do not share a database. Visa cannot do a two-phase commit across institutions it does not own. Instead, Visa uses a message-based saga pattern with compensating transactions. The authorization creates a hold. The clearing confirms it. If anything fails between authorization and settlement, a reversal message, ISO 8583 MTI 0400, is sent automatically. This is how Visa enforces ACID-like guarantees across independent institutions. Here's the state machine that governs every authorization lifecycle, from pending through settled or reversed. Stripe is not a bank. It is an acquirer processor, the layer between merchants and Visa's network. Stripe handles millions of transactions per day across 135 currencies. Its engineering stack is Ruby for the API layer, Java for payment processing core, and Go for internal services. Stripe's critical contribution is developer experience on top of Visa's Rails, abstracting ISO 8583 into a REST API. But Stripe's most important reliability pattern is its Idempotency key system, used to prevent duplicate charges when networks retry. Stripe's idempotency keys are scoped per API key, stored in Postgres with a unique constraint, and return identical responses for identical keys for up to 24 hours. This is the Stripe reliability guarantee that merchants depend on. Here's what separates payment infrastructure from every other distributed system. Visa processes 65,000 transactions per second at peak with 99.9999% uptime. 32 seconds of downtime per year. Every authorization completes in under 300 milliseconds across up to 4 independent institutions with no shared database. ISO 8583 binary encoding, 37 years old, handles 65,000 TPS because it is 10x smaller than JSON and 100x faster to parse. Idempotency keys prevent double spend at scale. Fraud detection runs 65,000 ml inferences per second inside the authorization window. Active data centers in Virginia and Colorado ensure zero failover delay resilience. Authorization and settlement are entirely separate systems. Money does not move at authorization time. Visa's network is proof that a 37-year-old binary protocol and 2 active data centers can outperform any modern cloud stack when correctness is non-negotiable. Next, we break down how Stripe handles payment failures and retries without charging customers twice. Subscribe, new deep dives drop every day.